electronic excitations, and on this slide it says Intro to Many-Body Methods. I suspect we're not really going to get much of that, but it was meant to be some comments that kind of lead up to trying to do something tomorrow, Friday, on GW and to some extent dynamical mean field theory, but not meant to be highly technical in any of the lectures, but more like connections and ideas about the things. So the first, let's see if this, get this working if I can. I forgot to plug it in. Was already something that I didn't have quite right on this slide. It says part repeated from yesterday. Some of it is meant to be for next time, and so there's some comments right at the beginning that are along that line. So, and I also wanted to say that several people asked where some of this stuff came from. I had equation numbers and things like that, and it's from my book, and I had been trying to sort of avoid that and say that, you know, original references and things that are more general, but it just got harder and harder, so I'm just going to have some things. It's just definitely from that book. So here's the thing I emphasized last time, that it's really a many-body problem. And so there's a real many-body issues to think about, but I don't want to be heavy on them. Just want to say, well, what will be the kind of things that's needed, and if you're not an expert, you don't have to need to know the details, but it's great to know basically what's the general ideas. So next time we want to talk about what's a quasi-particle and what's this GW approximation. But you can get the basic point just looking at what happens in a real experiment that's like photo emission. That's meant to be electrons in a band and an empty band, and a photon comes along and kicks out an electron, and you can see that the correlation of this lack of electron at this point with all the other electrons is in general different from the average interaction of electron with other electrons. So there's no reason that the things that seem to come out so well with density functional theory, the ground state that had averaged over everything, there's no reason that should describe this problem. And this problem should, whoops, that wasn't necessary to put there. This problem should involve having to look at the correlations of this missing electron, or if you put an electron, it's, you know, this extra electron with all the rest. And that's where you get some dynamical effects instead of just the static effects in density functional theory. But then this would be more for next time. The density functional theory still has a great role in all this. It's basically a starting point, or is in fact there's some pieces of it that already make a lot of sense. Okay, and this is one of those cases that I'd like to say we want to come back to in this introductory kind of way, to say that we do the density functional calculations with the local density approximation, and germanium is a metal. That's the highest occupied states and the lowest unoccupied states are same energy, which it shouldn't be, of course. Just disaster in a certain sense. But you do somewhat better density functional approximations, you can do better on that. But the real problem is a many-body problem, and it's quite amazing how well this so-called GW approximation works. So we can understand the basics of that without a lot of math. Okay, let's look at the next problem. Suppose we want to absorb light. In comes a photon, And this time it kicks the electron up to the next state, and you've got an extra electron and an extra hole. And that looks a lot harder, doesn't it? Because now you've got two particles to worry about, and you've got an interaction between them. So we know from this simple, not even quantum mechanics, that if you have a negative charge and a missing electron that's a positive charge, they'll interact with each other and make bound states that we typically draw in the gap because they're lower energy, and you get excitons. So that this would be a bound state of this added particle and the electron in another state, and the hole that is left behind. But in fact, there's another way to look at it that makes it look a little easier. That you can think of it as the electron is excited to another state, and that gives you essentially oscillations of the electron density, and oscillations is a function of time because you've given it some energy, so it's in an excited state. So let's look at optical absorptions, and now I'd like to talk about molecules or nanosystems, something that's confined and not a crystal at this time. And here's the kind of motivation. There are these beautiful things that have been made in the recent past that you can make little silicon particles, and they can go from cases that's pretty well established as 29 atoms surrounded by hydrogens. This is a somewhat larger case. Those are hydrogens on the outside to passivate them, because otherwise they're very reactive. All the way up to many tens of nanometers of size, or 100 nanometers, and they become optically active. You can absorb and emit light at these colors, and you can essentially get any color you want with different size silicon particles. And then there's many other systems, and you can attach these to other things. So they're really an interesting set of problems. So now let's talk about what happens if you do have optical absorption. This would be an electromagnetic wave coming along with polarization. You know, the electric field is perpendicular to the direction of the motion of the photon. And first, we'd like to talk about the case that's not, or I should have said this at the top. In a solid, you would have basically the problem of the dielectric function. The electric field times the dielectric function is a displacement function this would be viewed like an external field, and this would be the internal field. And the dielectric function is a relation. But these nanoparticles are much smaller than the size of the wavelength of light. So this is supposed to be a little particle and magnified here. And as far as that's concerned, it's like it's in a uniform electric field that's varying in time, and it has a dipole moment. So the problem becomes dipole moment as proportional to the applied electric field. Okay? So I'm going to make a contrast and come back to the solids later, but I'd like to contrast two systems. One would be the case where the wavelength of light is much smaller than the system, like a solid, and the other is the case where the particle is much smaller than the wavelength of light. And here's what you would get in following this exact same picture for a solid. We know we have a bunch of states in the nanoparticle that where you can excite electrons from the filled states to the empty states. And there, that puts the symbol with it. Then this would be the simpler way to look at it. It's just basically all you need to know to get the optical absorption is the dipole. You didn't need to know any details of those states, details I should say. You need to know something about the oscillations of this dipole, and that gives you the interactions, the light with everything, with all the complicated things that are happening to electrons inside. Right? Now I didn't say what was the frequency dependent of this thing, but you can see that dipole dotted into electric field is the thing that gives you the energy for the way this small object would interact with a light field. I'd like to go a little slower than last time and ask for questions. Like, why are we talking about this? Or, does it make sense? Any of those kind of questions. Everybody says there aren't any stupid questions, and that's exactly right, because everybody learns if you ask a question. Yes?
I was just wondering, because I mean the whole picture of having band structures is essentially like a single particle.
Good. Thanks for catching on to that.
So, in how far is it appropriate to talk about excitations in that way, anyways? Like considering a single particle picture.
I was hoping you'd ask that. Good. Because when I was saying it, I was thinking, oh, now I've already told you that it had to be correct in a many-body sense, and here I was drawing these one-electron diagrams. But what we really know in a 100% many-body sense is that if you pull electrons out of this system, then there are energies at which, discrete energies at which you can extract electrons. And so it's misleading to draw them as if there were electrons occupying that state, that state, that state. But nevertheless, when you pull one out, there's a whole set of possible energies. And when you put one in, there's a whole set of possible energies. And if you have both, then there's this combination of the possibilities to have, and that's the possibilities of optical absorption. It's when the electron is still on the particle and it's just in an excited state. So let's keep that in mind always. When are we using those concepts correctly?
Are these labeled as block states more than a single particle?
So when we go to a very large system, then we'd have to talk about that. Which problem are we making?
So isn't that almost a many-body thing? There's a wave packet of blocks of the eigenstates.
Oh, let's see. Oh, now I know what you're saying. I would say, let's just stick with eigenstates for now, and not worry about wave packets, which really would be transport of some sort. And so even the many-body system has a set of eigenstates, even though we may not be able to calculate them.
Isn't an exon a many-body eigenstate?
Is the exodon
a many-body eigenstate because it's the
yes.
single particle eigenstate can't localize first.
Right. So I think this is really good. So either this solid, and you take an electron out, would be, suppose it has n electrons, and you take it out and it has n minus 1, or you put in an electron, n plus 1, and those would just be the states of n electrons, or n minus 1, or n plus 1. If it's an isolated system, then n is a finite number, and you can really talk about it just more easily. You have the possibilities for pulling one out, putting one in, or just the possible excited states with keeping the same number. So this one we can kind of count. over here we use the n as a kind of a mathematical thing to carry along, to say n may be 10 to the 23rd, but we can always add one more. And it's different. In this case, with an insulator, that extra one electron is at a different state from all those, from the average of all the others. Okay? So that's a good reason I'm talking about these finite systems. So anyway, still, the states that you mentioned that are these states for the n-electron system was the ones that you could reach by optical absorption, and the charge is still on this particle. So time-dependent density functional theory is saying that just like the cone-sham problem, you can create this auxiliary system where in principle at least, you should be able to get, let's see what's actually here. You should, in principle, be able to get the exact states of the system if you have the right exchange correlation function. So it's just take the same logic as in the static density functional theory and carry it over to the dynamic. We'll say a little bit more about that in just a moment. But that's the bottom line. Sorry, I guess it's on the next slide, and that's supposed to be erased. Gosh, several mistakes. So anyway, just by definition, there's a potential acting on this system that's just the electric field times position. So that'd be the potential that would act on the charges in this system. And we can either think of it in time or in frequency. I think it's the next slide. That's what I want. Yes. So the Hardy Gross and his co-workers were the ones that invented, if you will, or showed that it was useful to do this time-dependent density functional theory. And people had to teach me, in fact, that what they actually found was current functional theory, which means that if you have, well, actually, it's right there. Electric fields and currents. That's also a way of expressing the charge response. And the way you would do that, and going back to basic quantum mechanics, would be to take a Hamiltonian, take its static Hamiltonian, and then you add E over C P dot A. So a vector potential. And do your perturbation theory in the vector potential. And that would be the relation of a current to an electric field.
Is that an eigenstate of Hamiltonian? E? Oh no, that's the electric field.
Sorry, I guess I missed the main point.
Isn't J history then?
Yes. Actually, that's what I was looking at on, oh, here it is, right there. I was trying to remember where it was on the slides.
I missed the bottom line.
Yes, sorry. I was going to get to the bottom line, which is that this one-to-one correspondence actually is one-to-one current at one time and electric fields at previous times. Now, we'll get to what people actually do, but this is a theorem that if you start with an initial state and then you evolve to a different state, that in principle the current at this new time is determined by the electric field at all the previous times.
And that's the external electric field, right?
And now it's the external electric field, yes.
So, on the face of it, that doesn't sound terribly powerful thing to say.
Doesn't. right? Okay, you're absolutely right. And it wasn't like density functional theory. It didn't sound very powerful, unless you got a good approximation, right? Okay, so we've gotten to that point, and now that might help you if you scratch your head and say, why did we talk about these small particles and make a difference with a large system like a solid? Well, this is what they used to make a time-dependent density functional theory. They just used the continuity equation. I couldn't find a symbol for divergence on the computer when I was looking. So anyway, it's divergence of the current is the density. And I suppose there's supposed to be a minus sign there. That the if you know the current, then you can find the changes in the density as a function of time. And that works for a finite system. Because if you have an infinite system, then the changes of density may be at the surface, and something that you don't want to handle. But in a finite system, there's basically no problem. If you know the current, then you can calculate the time-dependent change in density. And that's what's called a time-dependent density functional theory. But once again, you have this problem of the potential at all previous times. So what do people actually do? So as far as I know, right now there are theoretical attempts to deal with the fact that you had to do previous times for this exact purpose. And I think you can imagine how hard that is. Because if you want to do an absorption, something has been happening. You are at a resonance at previous times. And it's just really tricky. However, this would be almost the equivalent of static density functional theory. You make something that's so simple that it's easy to use. And the simple thing is you use the good old exchange correlation function that you did in the static case. And now it's an easy problem. It's just time-dependent equations where you have a potential that's evaluated at the same time as a charge density, and it's just an extra step of difficulty on top of the usual Cauchy problem, but it's a completely doable set of equations. So, as far as I know, this is exactly what's done with this work, and it's used a lot. In every chemistry code, all the famous ones that are used over and over, it's one of the major pieces because it improves the energies for these absorption frequencies, just major improvements. Okay, so here's an example of those silicon clusters, and now it's a figure that I had that's pretty similar to the previous ones. And this would be calculations, and this experiment on here. The experiment was only at the larger size, and the calculations tend to be at the smaller size. This was a few years ago. And we're comparing this time-dependent LDA, local density approximation, just the usual thing that we've done in static density functional theory, with two calculations that that really try to be many-body calculations. Hartree-Fock with configuration and interaction, and beta-salpeter, which is a many-body diagrammatic expansion. And you can see that basically they're agreeing pretty well. So there's a couple of reasons for this, and I will ask you some questions in a minute. This is a decrease in oscillator strength, I mean how much they couple to light. Can you tell me why you think the degree that they couple to light should decrease as a function of size? And it should couple better at small size?
Maybe if they're bigger, you have less surface atoms that can take part in the oscillation.
Okay, now that's correct, but why doesn't the bulk help you? The inside of this.
Because, I mean, the surface plasmons, they travel on the surface of the particle only.
That's right. I mean, you know better than I do, I think. Is there some other reason? I mean, it's what you're saying, but you can be a little bit more specific about silicon. Well, why is it that the laser pointers are not made out of silicon? They're made out of gallium arsenide or gallium nitride or... Right. So silicon doesn't absorb light at its lowest gap. And it doesn't emit light at its lowest gap. It just gives all its energy to phonons. And so if you go to very large size, then you don't have any surface area, right? Or it's negligible, and it shouldn't absorb at all at its lowest energy state. Or it's absorbed with phonon assisted absorption, but all that stuff is really weak. So this is why it was so interesting to get those silicon particles that would glow beautifully in the presence of either electronic stimulation or like ultraviolet lights, absorbing ultraviolet light and emitting visible light, just really strong emitters out of silicon. Oh yeah, I could have put this up earlier. The fact that this increases really is the first idea is this particle in a box. You've actually just confined the states. And that gets you the basic idea that how this increases. But then of course there's details on top that that really were important in the calculations. Here's some excitations in germanium clusters. And we worked on this with Monte Carlo methods. Now that's a pain. And it's because you can either do two things. You can put in an extra particle and just do the calculation, or you can take one out and do the calculation. Or you can promote an electron to an excited state. And in Monte Carlo, that's okay if the excited state is orthogonal to the ground state. If it's not orthogonal, the system will just collapse to the ground state, and you won't get anything interesting. So there were cases here where you could do it, and it's still a pain, because it's so hard to get these small energy differences. That's a hard job. And so here was a comparison of germanium and silicon, which are very different in solid, but in these small clusters, they're pretty similar. And one of these is time-dependent density functional theory, which is, by my standards, pretty good agreement. See, these numbers are like 8 electron volts, 6, 4, and so that's less than 25% error, which is good in these systems. So, question would be, why is this so good? We made this horrible approximation that it's just the same functional as at the ground state. why was DFT so good in the first place? I don't think I said this yesterday, but I wish I had. To me, the first steps, the thing that just made cone and sham work so well, was that they took care of the big terms. You just got to get the Coulomb terms right to get reasonable energies and materials. So you got to get your density roughly right. You just got to get the kinetic energy of the electrons, and so they got the kinetic energy of non-interacting particles. And then on top of it, what was left over wasn't too much. So that you got rather good results. And I say that's the same in time-dependent DFT. And the basic point is there's a big Coulomb interaction between the charge that's positive on this side and negative on this side. And so you capture that big energy difference, you know, the big energy effect. Let me see what's next. So now we're saying everything's a lot better, but what's it better compared to? Better than what? If you have a density functional calculation, what would you do to calculate the energies of excitations? What was that?
Look at the single electron ion values, perhaps corresponding to a
What, the electron background, did you say?
well, let's look at the ion values.
Oh, yes.
Maybe
You said it. It's exactly right. Because you do this calculation and all you've got is density and you've got those eigenvalues. And we've said they didn't mean anything, right? But that's all you got. So people do this, right? And say, so here's our particle, and we've got now independent particle picture. So now we've gone away from the correct picture, and we're just going to say, now we have field states. Just really non-interacting electrons that's supposed to be down. And we take one out. And the energy difference is just the eigenvalue for this highest occupied molecular orbital. And we have these empty states. If we put one in, it would be the eigenvalue for the lowest, whatever that is, lowest unoccupied molecular orbital, and say, take the difference. And now you can see what's the difference. In one case, these are eigenvalues of just the original potential within electrons. Where you have n is the number of electrons you have, and you've just done something that's really pretty bad for a small system. You take an electron out, but you don't change the potential. You don't let any of the other electrons relax. It's similar to what we had for neon yesterday. You had the energy off by a factor of 2. If you put one in, you put the electron in without letting any of the other electrons do anything, and you didn't take into account that now it's a charge system. Whereas, and if you were to excite from a hold and an excited state, you would just get the difference of eigenvalues, and you wouldn't have any of this effect of the large charge on one side and two sides, plus and minus. So that would just be missing completely. So what this has done is it's put in something that's really simple in the complete spirit of the original cone and sham method, and it's done it in a way that's now become exceedingly simple to do in practice. Let's see. I want to talk about the actually doing something, but one more thing on that. We did some calculations with this time-dependent density functional theory, and just turned off all the exchange correlation. Just treated it like it was just charges, and in fact you get a pretty similar answer. So the triple reason why it works is that those effects were pretty small anyway, and the Coulomb effects just dominated. Okay, let's keep going. There's two big methods that I think are both interesting. One is that you just simulate the problem in real time. You just put a field on and you watch the charge density progress in time. And the other is you make a linear response, which is you do perturbation theory, and work out what happens at particular frequencies. So this is mainly in frequency space, and that's mainly in time space, and there's Fourier transforms in between. In the top one, you can get nonlinear terms easily, and it's hard to get linear terms because you have to extrapolate to small potentials. So I wanted to say this piece that gets to, this will help us for the future, for tomorrow, is let's go back to what happens for an oscillating dipole or for an oscillating density. It's really just a harmonic oscillator, right? It has excitations, and so let's look at the oscillator problem. If we have a force that's proportional to displacement, then the equation of motion for the oscillator is second derivative of the position. It's a force times position. So K is a force constant. And generally we have a damping term and a driving term. And if we do the Fourier transform of this, then to get the response of the system, the position of the particle as its frequency, the displacement as a function of the driving force, it's just very simple to just Fourier transform that equation and get to this one. It's basically has 1 over the differences of squares of the frequencies and the damping term. Now, is that familiar to you, that you have this complex damping? Yeah, right. You got that a long time ago. So basically we would expect in this problem that we would have some kind of resonance at some excitation frequency, which is not the same as independent particles, but it is from the ground state up to some excited state. And it really should have the same properties as a harmonic oscillator. Oh, and now we can see some of the, let's see, sorry. Oh, I don't know if I got this mixed up or not. Excuse me. I swear I got some things confused on which words were on which slide. Okay, harmonic oscillator. Something got missed. Well, okay, I'll just say, and you can already see it here, that was the point of this. Forget that thing at the bottom. The point was that this had a negative sign, and so the sign of this term determines whether it's exponentially damped or exponentially increasing. You're putting energy into the system or you're taking it out. So let's just keep that in mind. Whenever we have any kind of damping, that it needs to be a damping and have a particular sign for this imaginary part that's added. Depends on the how you set up the equation, whether it's plus or minus, but you always have to have, you know which sign it has to be. And that's guaranteed by these Kramers-Kronig relations, which is a response of the system in the real part and the imaginary part. We just go through a formula like this, and we'll see that if you take the real part of the equations, the real part of this susceptibility, and the imaginary part, which is I omega gamma divided by the absolute value of squared of the denominator, that it will satisfy these conditions. And even when the damping becomes some complicated thing and not just a simple constant damping. Sorry if that wasn't clear. So now let's get to the one we care about, the response. And we care about the change in density with an applied potential. Now that's what we want to work on. And this response can be written either in real space or in Fourier space. And it's in general, when you apply a potential at one point, you get a density response at another point. Because the potential acts on a charge at that point, but then that affects charges at other points. Okay, now let's think about what we have in a Cone-Sham problem or any self-consistent method like Hartree-Fock. Yes?
Is it only correct to write that in Fourier space? Is it not?
Is it in?
Is it not convolution in real space? That isn't it? It must be in Fourier space that identity is right. But for real space, does it still work?
Let's see. Let's be clear what this means. And I admit I left off the slide what that actually meant. So it's the derivative of n with respect to v. It's not actually the ratio.
Okay.
Thank you. And the reason it's that funny delta symbol is it's a functional derivative. Because you're differentiating with respect to something that's varying in space. Thank you for clarifying. You can think of it as just a derivative at one point with respect to the potential at another point. You were right, what you said. Okay, but in one of these problems, we have something like, we want to use equations that are Hamiltonian, it's minus plus the potential, and in these systems, it's this effective internal potential that goes in the equations. But what we want is the response to an external potential that you've applied. And this potential is the external potential plus all the internal terms. That has to do with internal charges, exchange correlation, all that. And we want to get this one. So if we look at the, right, excuse me. So the way to look at that you can do really easily is say, I can calculate the change in charge due to the effective or the internal potential. That's like the Cone-Sham potential. Because I can just solve this equation. If I change this potential, I can get the change in density. So that's something that's definitely doable. And I can use a chain rule. How much does the effective potential change when you change the external potential? And finally, that can be written in a form that's like this. Using the chain rule, you wind up with the function you want inside. So you have the real susceptibility is this zero-order susceptibility. That's just the effect of the effective potential, and a factor that involves the original susceptibility, and this factor k that you can work out, because it depends on the Coulomb terms and the exchange correlation terms that then have this name, FXC. It means the extra stuff from exchange correlation potentials. And if you have a functional, you can just work it out. Now, solve that for the chi, and you get this nice expression. Chi naught, the thing you can calculate, divided by 1 minus chi naught times the k. And this is exactly the thing that's called a random phase approximation, and this used in many, many places. Yeah.
So the exchange correlation function up there, that's the reason why that is not time dependent is because of the adiabatic.
Exactly.
Because otherwise you would have time dependence there.
It'd be horrible, right? and I actually pulled this out of a place where it was not time dependent, but with our approximations, it's still what we actually do. Yes.
So why is the random phase approximation actually called random phase approximation?
That's a good question.
Approximating well, phase of wave functions.
I think nowadays it's really sort of strange. It sounds like you've done something that's random or stochastic or something like that. But in the original name, I think, came from Pines and Bohm in the 50s. And what they meant was that if you have interactions between all particles, they sort of average out and you get this one average interaction. And that was that's how I understand the way they came up to this meaning. That you can, in quantum mechanics, you have phases of all these possible things that can happen, and that all the, complex phases in the sense of in an exponential. And they would average out except for the average. And then that became really important in Coulomb problems, because the average is this Coulomb field that you just have to get right, or otherwise, you're just dead. So it kept that term and then threw away a lot of the other terms. And then this is used in essentially all forms that's essentially these self-consistent type calculations. So I know I'm going slow, but thanks for asking questions. There's a really clever way to do the time-dependent density functional theory, and so I'd like to go through this kind of quickly. Here's the expression for the density, and this would be the change in density with the change in these quantities, the wave functions, with a factor of 2. If you think of the problem as the Hamiltonian, the original Hamiltonian, the static one, plus this extra term is, that's the real Hamiltonian, divided into 2 parts. The left-hand side has the original part that was, before you added any perturbation, and the right-hand side would be the perturbation. You just put it on the right-hand side. The eigenvalue changes, and there's a perturbing potential. And then you can write this in the form of excuse me. Oh yes, then this would be the relation of that perturbing potential to the external potential plus the stuff that's internal. And the usual textbook form would be you just do perturbation theory. You expand in the eigenstates of the system, and the perturbation mixes your lowest energy state with all these excited states, and you get an expression that involves a sum over excited states that gets to be just horrendous if you have a very large system. You get huge numbers of states, and that is just an enormous problem if you get to large problems. But there's a way to do that doesn't have any excited states. Just you don't have to deal with them. Oh gosh. Oh yeah, this is the whole story right there. It's essentially time-dependent density functional theory. What you do is you think of those equations, those 3 equations, as a set of linear equations for how the density varies when you put on a potential. And that means your wave functions change. So in fact, they're mixing in the excited states of the original Hamiltonian, you're accomplishing the same thing, but all you have to keep is how the actual density is changing. You don't have to keep all the information about all the excited states. And this gives you the change in density as a function of the applied field. So there's some nice review articles, and I have a reference at the end for things like this. It's really very pretty, and it's now used quite a bit. Okay, and the real-time problems, I worked on this some, and so I know something to say about this. You could apply a potential as a delta function and get the response, see what happens. Or you can apply a step function, like this would be the analogy of a harpsichord, where you have a string and you pull it and then you let it go. And so this would be put on an electric field and then suddenly turn it to 0. And see what happens later. And you can see that you can do either one of these, because if you take the derivative of what you did with the step function, you can get what would happen for a delta function. And you can see also that the delta function is easier to see, that if you add up a whole bunch of delta functions, you can get the response to a lot of many different possibilities. So this is the getting these responses is then allows you to get a lot more than just the response to those particular forms. So whenever you want to solve the time-dependent Schrodinger equation, now instead of the harmonic oscillator, it's linear. And formally, the solution is an exponential. E to the I something. And the something is really complicated over time. But if you break it down into short time seconds, product of e to the I delta t times the Hamiltonian, then it becomes simple. It's called the Suzuki, misspelled, Suzuki-Trotter breakup, is to consider this the action over a very short time difference, where you can approximate the potential and the kinetic terms as constant. And gosh, I can't even read it myself. Okay, I made it a little more complicated than it needed to be. It's just convenient to split it in this form with the kinetic in the middle and half the potential on each side. That helps makes the error a higher order. And then what one actually does in calculations is one of two things. Just expand and make this time step small enough that the higher order terms are negligible. This is done in some of the current methods. And it has the problem that it's really not unitary. You evolve and the norm of your wave function changes because you've neglected you don't have a real exponential, you have an expansion. But if you have that time step short enough, then you can do a calculation and not have a problem. Another way is to make it explicitly unitary, which means that if you act on the wave function, you preserve this, you keep, well, actually you have a whole set of wave functions, right, with many electrons, and you keep them strictly orthonormal. If you choose your operators carefully, and this is one possibility, e to the plus I h on the top, excuse me, minus on the top and plus on the bottom, and if you just look at this and you see that the modulus is 1, because the top is just the complex conjugate of the bottom, and that's sufficient. So anyway, this is what we did, and the trouble is it involves an inversion of an operator, but if you have a small basis, that's not a problem. And So here's what we did. Argyrosohedus was the one that actually did it for C60 molecule. Have a step function up to a point, and then you turn off the field. And this is how it rings as you go to later times. Before you transform that, you get some of the major peaks that actually agree with other methods. And you see that time step is exceedingly short, which is what you have to get to follow the electrons. So this really does capture the basic properties in this low energy range. The high energy range is garbage because two reasons. It's hard, you have to take very short time steps, but even worse, we have this localized orbital basis set. I didn't tell you that. It's written right up there. That doesn't allow the electrons to leave. And that's just not true at high energies. You just kick off electrons. So you kind of have to think about what you want for how you do it. Anyway, if you do it with other bases, you get very similar results at low frequencies. And right now, probably the most used code that you can get on the net for free is Octopus that works with functions on a grid. So you update as a function of time functions on a grid. Okay, where I can stop. Except I won't. Let me see what's. Okay. Think about this. Why didn't it work in a crystal? Now let's take a break. And we'll mention that when we come back. Okay? Okay, and be thinking of any other questions too.
Right, shall we come back at 3:15? 15 minutes of break?
Nothing.
You don't have time after.
They're not localized. Now, why would that make a difference?
You don't have a common process with the spring force for storing.
Well, you don't have it the same way, at any rate.
Yeah.
Anything else? Okay, I should do this quickly so we can move along. But remember that transformation that started with currents and got to density. If you think of the small particle, small system, I should say, where you really are treating the whole thing. You're not, and some of the questions help me. So it's a finite system with open boundary conditions. So the particles are trapped there, and you have this density oscillation, and the current that flows, and so you really have the whole system. And the dipole moment I talked about is the dipole of the entire system. And then that couples to an electric field. So there's just a dipole dot electric field term in the total energy. For solid, on the other hand, we would like a method that looks at one unit cell in the presence of this infinite crystal, and we get a problem. Let's go first to the case where you really can do it, and it works. It works rather well for some experiments that look at short wavelength. So suppose you have a problem in which the change in density is on a scale of a unit cell. So suppose we have a few unit cells, and we have a charge density that's varying something like this. So this would be plus, minus, plus. Then you really have the same problem. You just take current and invert it to density. Use the divergence equation. And everything is nice and local, and it works. And there's electron scattering experiments, not photon absorption, but scattering that transfers a large wave vector, and the approximations work out, and it's essentially as good as these small systems. But if you have a large system, a long wavelength that's much larger than the size of the unit cell, in this argument about the current flowing, now I turned it horizontal, sorry. So the electric field and the current would be horizontal in this case. You can see that it's really hard to look at the density and see what the current is. It's impossible. I think that's a true statement. And actually you can see why it's impossible. Think of a homogeneous system. Can you look at the density and say whether there's current flowing or not? Right, okay. So there's some things you just can't do. And so you would have to put open boundary conditions on the solid, put in the surfaces, and then you could work it out. But that's not what we wish to do. So that's one of these problems that leads up to a whole lot of other associated problems for current and charge in a crystal. I'd love to talk to anybody about that would like to. I'd like to make just a comment now, and there's a bunch of slides, but they were meant to be extras. When would you care about adding and subtracting particles and electrons in these nanosystems? Optical absorption, you don't care. You just promote them and they're still there. Here's the case. These are really interesting problems. You wanted electrons going through a molecule, so these ideas of molecular switches and transport through one molecule. Basically that involves an electron getting on this molecule and getting off into the metal on the two sides. And that leads you to a bunch of interesting problems that there's not excitations of the molecules, but adding electrons and then going through the molecules. So there's a whole bunch of interesting problems that come up in this and fields like this that are really interesting. Okay, I'm going to turn this off and go into the next one. If you've got any questions.
Sorry.
Yes?
About DDFT, can you get exodonic states, right? I've heard that there are some problems with that.
You got it. And there are problems in the sense that it is exactly what you said. In these small systems with open boundary conditions, the electrons and holes they're trapped near each other. And if you try to describe an exciton and a solid in terms of these cone sham wave functions that are extended, you really just don't get excitons. It's another way of saying a problem in a crystal.
Yeah, so it's a consequence of that.
Right. So it's really funny, isn't it, how it just, you get trapped by things that you can justify, but for certain reasons, and then it just doesn't apply in other cases. Good. So I wanted to talk about mechanical properties, because this is something that I like, and it's come up in some of our discussions. Again, I have more slides than needed, so I'd like to sort of get to what I think is the points that I could add something. So the equilibrium structure of a material is determined by the positions of the nuclei. I'll just say that's essentially the definition. And the for small, for any system, then it's determined by the 3n, the degrees of freedom for the nuclei, minus 3 for translation and 2 for rotation. Let's say the energy doesn't change with translation or rotation. So you can specify all the relative positions in terms of 3n minus 5 variables. But there's a big difference between n that's a few and n that's 10 to the 23rd. And so let's see. So for a molecule, and I think a lot of you are doing calculations in which you do density functional or you do something else, and you relax to get the structure. And you get the structure for the case where the forces are 0. That's any minimum, and you can hope it's a global minimum. But what can you do? Work as hard as you can to be sure it's the global minimum. And so in principle, this is easy, and you accomplish it by many techniques. Steepest descent, conjugate gradient, molecular dynamics in which you remove the temperature so that it gets more and more closer to the ground state. Many ways. But the idea is to get it to where the forces are 0. What do you do for a solid? Here's just a picture of some crystal. And what you do is for any atom in the unit cell, you require that the force be 0, or it would move in the unit cell to a different position. And of course, in every unit cell, it has to be periodic, so you only have to look at one cell. But that's not quite all. The entire crystal can change shape or size. So you would like to know the positions of the atoms and the volume and shape of the crystal at equilibrium conditions. So somehow you have to change the volume and shape. Or you also want it under pressure. That's an interesting problem. What happens to materials under pressure or under shear strain? So you'd like to be able to deal with the degrees of freedom in the unit cell. So that would be 3 times the number of atoms in the cell. A nice small number. And you'd like to minimize with respect to the volume and with any shear strains. So any kind of change of shape of the system. And then I want to say, well, let's look both at the case where it can really work it out, which is a crystal, and then keep in mind that we might want to look at systems like this. It's nanosystems. It's sort of like a crystal in the middle, but a whole lot of surface area, where it's not like a crystal. And just be thinking now. Is it more like that small molecule, or is it more like a crystal? So let's get to the forces part. This would apply to the small molecule or to the atoms in the unit cell of a crystal. And how many of you have been through this Hellman-Feynman theorem argument? And many have not. Okay. It's so pretty. The idea is that you want the force on a nucleus in this case, but it really can be much more general. Generally applicable in many problems. And you know that force is minus the derivative of energy with respect to position. know that energy is the integral of the expectation value of the Hamiltonian. And you know that the Hamiltonian is something that depends on the position of the nuclei, and in the direct Coulomb problem, it's really sum over 1 over positions of electrons minus position of nuclei plus everything else. Everything else. And just to be clear, let me add one more term, and everything else is going to be in the middle. All the other nuclei, too. The 1/2 and the sum over all the other nuclei. And everything else is really complicated. Right? There's all these interacting electrons, all that stuff. But the only thing in the Hamiltonian that depends upon the position of that nucleus, whether we call that nucleus I, are these two terms. And everything else is kinetic energy of electrons, the exchange correlation, and they change when you change the position of the nuclei. The electrons, wave functions change, all that. But the theorem is that that's equal to the wave function that's unchanged and the derivative of the Hamiltonian with respect to position where this is the wave function that's not changed at all, just the ground state wave function. Even though you know the system changed a lot, when you move to nucleus, you ignore it. Now, is it obvious why that should be true? Maybe it is if you've done it. Probably not if you haven't done it. But it would be true in any kind of mechanical system or whatever. If you take all the other degrees of freedom in the system and you say they're at equilibrium. Because if you do this derivative, then you should get terms like this. Derivative of the wave function with respect to position. And then another derivative is a complex conjugate from one on this side. And the point is that's 0 because the wave functions are already at equilibrium. And there's another way you could really see that it's 0 is take the derivative with respect to the nuclear displacement of the norm of the wave function. That it does not change. You don't change the number of electrons. You don't change the number of nuclei when you move one. And, oh yeah, notice that then this would mean that psi star derivative of psi with respect to r plus the complex conjugate is equal to 0 because the derivative is 0. And I just took the derivative of one side and the other. And since psi is an eigenstate of H, then you can let through and just say it's 0 by conservation. Work that out for yourself. That one too fast. Yes?
Something I always wondered about is whether this was true for higher derivatives of the term.
No, it's not. As far as I know, I don't know of any way to extend it to higher derivatives. There's the tricks that you can make a higher derivative simple. Simplify, I should say. I think it's only the first derivative. The Anybody knows different, please tell me.
Is one assuming that Born-Oppenheimer approximations when put in this theorem?
Yes. What you really assumed is that the nuclei were completely static. Now, you can actually extend it, take the quantum states of the nuclei and prove something that's very similar, be like the center of a wave packet for the nuclei. But the way I've done it, at least, it's just the nuclei are fixed external objects. Anyway, I think that's a pretty statement, pretty theorem. And one of the, I got a little story about that. This was done by Hellman in a textbook in the early 1930s. And it was something that's, this took this long to write it down, and it was known. How did he get the Feynman's name attached to it? He wrote a paper when he was an undergraduate that basically proved this, but apparently he was the first one that realized that the consequence of that is that the force on the nucleus is just the charge density of the electrons acting on the nucleus and the other nuclei, just the density, nothing complicated about them. And that's because you take this expression, and the only way that the Hamiltonian depends upon the position is through this Coulomb interaction, and the psi star psi is just a density. So it really became a very simple idea. You just look at the electric field on the nucleus from all the charge around it, and that's the force, independent of all this complicated electron stuff. So that paper is written in '39, and it doesn't have a single reference. Well, as an undergraduate, you might think, well, that's okay. So Conyers Herring, one of the well-known people in the field, I asked him about this, and because there's an acknowledgement to Conyers Herring in that paper, and he said, well, he thought that all theoretical physicists knew about that at the time, except maybe those at MIT. Okay. So now let's go on and say there's a big problem with this. If you use general basis sets, and plane waves are wonderful. And it's because you can see the problem. If you actually move the basis, like functions that are attached to the atoms, you're going to get something else. Unless you have an absolutely complete set, then the fact that you move the basis will actually add some extra terms, which have got this name Poulet terms, and they just complicate your life. They can be put in, but it's a mess. And plane waves don't care where the atoms are. They just sit there. I mean, they stay the wave vectors stay the same all the time. They're just waves. And so you don't have any of those terms. And so the plane wave codes and the grid codes can really be far simpler. So now, forces are useful because you really want to be able to do things like relax the atoms, or if they're out of equilibrium, you'd like to know what is the force. And if you do energy, you get one energy. If you do forces, you get 3n numbers for n is the number of particles. So you get good information. Now, what about the stress? What about the pressure? Or what about the volume or the strain? The basic idea there is that here's a crystal, that's a simple crystal, where in that structure there won't be any forces because every atom is a center of tetrahedral symmetry. If you push the atoms off the sites, there will be forces. But just by building the crystal, you've already guaranteed that the forces are zero. So you don't have to worry about forces for this crystal, but you do need to worry about what's its equilibrium volume. And is it, well, I guess in this, as long as it's cubic, you don't have to worry about anything else. But you'd like to know, is that the lowest energy structure? So you should look at some non-cubic structures. And now I'd like you to think about, how does, well, first, I guess I'd better say, you'd also like to get the volume as a function of pressure. You'd like to know what's the bulk modulus, or the compressibility. So you don't want to know it just in the absence of any effects from the outside. You'd like to know it as a function of what's pushing on the material. So what would you think about? You actually put pressure on something by pushing on the atoms on the outside, and that transmits the atoms on the inside. Is that a good way to think about it? Certainly true. Is it something you'd rather do than worry about how the pressure got to the inside?
That doesn't mean it to be isotropic.
If it's pressure, it'd have to be isotropic, but it doesn't have to be. You know, I tried to draw a crystal where it's not obviously isotropic. And this is a highly schematic. You have to have forces from both sides, and the total is 0. But somehow you've got to get you're pressing on it from the outside.
Should you think of moving the nuclei to create opposing forces to the ones that are applied?
Right. So for sure, you push on the outside, and it transmits forces back down inside. The guys inside push back and transmit it all the way back to the surface. When you think about that a while, you'll find that you get all mixed up. Did you know that stress or pressure is a force per unit area? And you know, and this is what you know, if the crystal is large and you apply a simple pressure on the system, then it's isotropic. Sorry, it doesn't have to be isotropic. It can be non-isotropic, but it's the same in every unit cell. Okay? Now that's of course not exactly right if you have a funny shape and you press on it in different ways. But as far as as one unit cell would find, the pressure or the stress should be essentially the same on that microscopic cell, because everything else is on very slowly varying. So how can you get things from one unit cell? So what you know is the surface may do funny things, but when you get down inside, there's a very simple thing that will happen. The atoms will get closer together, or they'll shear or something. But that's all that happens. I mean, that's what happens down the inside. Oh, that's just a definition of strain. What you mean by strain is a displacement from some equilibrium positions that is a tensor, and by symmetry you get it down to 6 independent numbers. Okay, there's a stress theorem, and it's really the same as the Kalman-Feynman theorem applied in a different case, and it's the same as the virial theorem. Who's heard of the virial theorem? Ah, good, lots of hands. So that's for a liquid or a gas. You can find the pressure just by the inside of the material, just by its density inside the material. And I have an example that's the simple expression. And that's in the thermodynamic textbooks. That for quantum or classical systems, you don't really have to know where the pressure came from. you can just look at any representative small part of the system and find out what is the pressure that's being exerted on that system. And you find it out by how much pressure this is exerting on the rest of the world, which is they have to balance. This is the stress. Let me say one more about that, have to balance. Let's think about a classical system or gas. The atoms are bouncing around and they're hitting the next atoms, and basically the kinetic pressure is always outward, because when you try to bring things in, they're at a given temperature, they're just bouncing more and more off of each other. The potential energies may be pulling in to balance the kinetic, or they may don't quite balance it, which would correspond to pressure from the outside. Okay, let's go ahead. All we have to do is realize that a stress is a derivative with respect to strength, just like a force is a derivative of the energy with respect to position. That makes sense? In elasticity theory, this is it. So I don't have to belabor that. But you strain it, the stress is the reaction force that's per unit area. And this is a pretty part of the way of thinking about it. That's what's in the Imperial theorem. If you think about down in the inside of the crystal, and you think about what happens if you strain it, the simple idea is just the volume. You just pull it, just increase its volume or decrease it by a small amount, and you'd say this would be a way of producing a finite. If you do a finite change of space, it'd be a finite strain. So it's like you take every particle and you move it a little further from all the rest of the particles. And that's exactly what's in the Imperial theorem in the thermodynamic textbooks. Wait. Okay, that's it. I had another little anecdote. That was this is in my book, and this is the title of one of the appendices, and my family said, "Boy, that was a good title." Maybe you'll feel that sometime too. So, stress theorem. The Imperial theorem is just volume and pressure. It's not uniaxial. And what you find is that you scale space, which means you pull particles apart or push them together. And the kinetic energy always scales like 1 over a distance squared in quantum mechanics. You can change that in other systems. The potential energy, if it's Coulomb, all the energies go like 1 over a distance. And rigorously, you get to this result, that take the derivatives of the energy and you'll get 3 times the pressure times the volume is twice the kinetic energy plus the potential energy. And you might sometimes see this written as with a 0 on the left-hand side, that the potential energy is twice the kinetic, or minus twice the kinetic, or Coulomb system. And that's just the condition for equilibrium at 0 pressure. This is the more general expression. So if you know the kinetic energy down the inside and the potential energy, then you can calculate the pressure. And the reason it's, I'll get you just a second. The reason it's the same as the Helen-Feynman theorem is this point that what you changed is the relative positions of the atoms, and you know for sure that the wave functions change a lot, but they were already at a stationary point. And so all you had to do was change the distances between the particles that affects the terms of the Hamiltonian, and you didn't have to worry about all the details of the electrons. Question?
Is this theorem valid for any case?
So take a system that's in equilibrium, and this particular case is for a Coulomb potential. That's the only time you get exactly this one. But in the textbooks, there's virials for other kind of potentials. So you can find virial theorem for different kind of potentials. And if you want to do stress, then you just have to do the same thing, except that now you can have a shear, and I guess on the previous slide I said pressure is all you have in a gas or a liquid. So that's all you worry about, and that's all that's in the thermodynamic textbooks. But if you have a solid, then it has a shape. And so now you have to worry about changing the shape. And really, it's just as simple. And I didn't actually look up the exact form, but what it is the expectation value of a kinetic energy. So kinetic energy in quantum mechanics is a second derivative of a wave function. But for an xy component of the stress, you need the x derivative and the y derivatives in the kinetic energy. And then you get potential energy terms, and rigorously, the only potential energy terms in a solid are Coulomb interactions that are pairwise, just between pairs, and it's very simple to work out that the virial, this is the same as the virial, except it's anisotropic. The force in the x direction, that's a function of the, so the force on atom I due to atom J, in the x direction, dotted into the vector between I and J, and the y, no, that should have been a dot. It should have just been multiply the x and the y terms. I have to correct that. It's not a dot product. That was wrong. It's just the product of force in the x direction, displacement in the y direction, and you calculate the stress. And you can get that from just down inside the material without any, you just don't need to know our surfaces. This is the basic expressions that you can then get to find the structure of any crystal. So if you go to these programs, all the good programs now will have forces and the expressions for the stresses that then will allow you to equilibrate the crystal for positions of the atoms in the cell and shape and size of the crystal. Any questions?
So this sum is over all atoms in the crystal or over all atoms in the unit cell? Or they can be equivalent like an imperial system?
Oh, good question. And actually, I forgot something. You reminded me. So this would be force on atom I, but you have to sum over all the atoms in the crystal that are active on it. But it's periodic, so it would be the same. If you take any equivalent atom, you get the same. But the forces may come from a longer distance. I have to admit, even when I was writing this down, I forgot a point. In density functional theory, it isn't of this form. Things are simple when you write them in completely general form, as a rule. And when you actually try to get something that's more like you work with, then like in density functional theory, you just have a density. You don't have particles. Then what do you do? It's not like the virial theorem in the textbooks anymore. I think that's what slowed people down from actually doing it. But I can give you a really simple way to see what you do. I mean, like really simple. If you look in your, and some, yes, please.
So to finish your point, because this is sort of tangential. So.
Well, okay. Then if you look in your computer code and find out where does a lattice constant appear? It appears somewhere where you define the shape of the cell. If you're doing plane wave codes, it defines the reciprocal lattice vectors. Where else?
And the potential energy term for the nuclei.
There's some potential energy terms that would depend on volume, right? Is that what you?
Yeah.
Yep. But just look where it explicitly depends on the lattice constant. And it might in that case, but it might actually just... And then use the Hellman-Feynman theorem just to say, I have a computer program that will give me energy as a function of lattice constant, or any of the three lattice, A1, A2, A3 vectors. And I take a derivative. Pick one. And it's exactly the same logic. You just go find what depended on this parameter that you're looking for. Take the derivatives at every appropriate place in the computer program, and that should be the answer. Now you got a question or comment.
This is slightly strange, but if you put something under high pressure,
Yep.
I mean, I might expect this sort of crystal symmetry to change. You know, it might under extreme pressure change from, I don't know, HCP to FCP or something like that.
Excellent. You got to deal with that separately, because I think it would be clear if it's in the FCC structure that you just can't get to a different symmetry unless you allow the program to do it. And so I think the bottom line is that this is one of those cases where you just have to test different structures. And if one's lower at one pressure and then another pressure is the other way, then there just has to be a transition between them. And so we find that, you will find it all the time if you do these kind of calculations, that you can go from one structure to another as a function of pressure or some other variable. Okay, this is going all right. So this really gives you the picture of what you can do to get the structure of a crystal if you do the electronic structure calculation. And I put a comment at the bottom that says, suppose you have a spatially varying stress field. Is that a meaningful quantity? And that's a real question that a number of people have worked on and still has yet to show that it's of any real use. But perhaps it will someday. If anybody wants to ask me, I'd be delighted to talk about it. Okay, somebody here told me they were working on a problem at least related to this. So let me just go to the next picture. There. It would be like a cluster of material that's grown on a substrate that's not matched, lattice matched, so you put it under strain. And you'd like to find out what happens. So if it was a tiny little molecule, you'd just relax the forces, right? And if it's 10,000 atoms, what do you do?
Dislocation.
What?
Dislocation.
Dislocation. Okay, there you go. So you have to start making some assumptions. Would there be dislocations at this point to relieve the stress? And if there's not, then you'd have some gradual change of the positions of the atoms. And I suppose if it's really big, you know what to do. It's just continuum elasticity theory. And you just don't worry about anything else. Or you have defects that are restricted very close to the boundary, and then up above it's just continuum elasticity theory. But if you have one like is shown here at the right, that's not 10,000 atoms, but some number like this, then it's not so clear what to do. Let me go back and see if there's anything on this slide. Okay. This, all I wanted to do here was to set up something I'll come back to. Suppose you wanted to relax those systems to the right that are biomolecule systems. So really the bottom line is there some way we can divide the problem into something that's a lot like a bulk and something that's or like an inside and something else that's different, like a surface. And I'd like to say that it may be that computer programs have gotten so good that you just let it go. At 10,000 atoms, you just have it do it for you. But even if that's true, you should think about it. So let's at least go a little bit further. It depends on the problem. I'm sure that's true. But let's think about some ideas. If it's a polymer, I think you might imagine that as a function of, say, stretch along its axis, that's just almost the same as a uniform strain. And it's really better to think of it as just a stretching of the crystal instead of pulling on this atom, which pulls on this one, which pulls on that one, which pulls on that. You see what I mean? If you do it by an iterative technique that works only on forces, then I stretch the polymer, and down here there are no forces. The only forces are on the edge. And it's only until this atom moves that there's a force on that one. And it's only when this atom moves there's a force on the next. So if you could just do that just by expanding the whole thing, it makes a lot of sense. These others are way more complicated, so they might have some pieces that look like that. And I have a suggestion for what to do. Go to the web and look up the name of Peter Poulet, the same name that appeared in Poulet forces. He's really done some very clever things, and I have an abstract on the next slide that's too long to read, but it makes the point. The real, I mean, there's a general way you can do it that works for any number of atoms. It's the Hessian, the second derivative of the energy, so that helps you to know how far to move when there is a force. Okay, that's still very general. And what he defined was generalized coordinates that were really useful. And the generalized coordinates would be, you can think of it as whether you'd like to move an atom at the time or a group of atoms at the time. And I make a comment that exactly the same ideas appear in how when you move the electrons around to try to get convergence as quickly as you can. When you do an iterative technique, do you change a part of the wave function at the time, or do you change the wave function? Anyway, it's highly related, and just be thinking of these things as related. And here's an abstract of a paper by Poulet that's year 2000, and he mentions 9,999 atoms, which is kind of a curious number, but I think at that moment in time, this was a big number to be doing with real electronic structure methods. And anyways, an alpha helix or something. And the sense was how you look for generalized coordinates that make the most sense. And so I'm proposing to you that you look for things that will really make sense for your problem, and you know, not just let the computer go and try to find the answer. You can go all the way from a crystal where you just have to make, you can't deal with all the atoms, but you have a really simple answer. Small molecule where forces is just the way to go. And then in between you can learn a lot about what would happen and kind of understand what's going on by looking at how atoms move to get the optimal geometry. Now I had some extra slides that were just to point out you know, what you do in problems like this. Can you guess what that, why this is related to the comments I was just saying? These are really interesting problems. People can pull one atom-wide chains of gold. Well, would you rather deal with all the gold atoms in this outside, or would you rather deal with something about the molecule and get the effects of the gold on the outside? It's clear what you'd like to do, and at least as far as structure is concerned, you should be able to model that molecule as just a bunch of atoms that has an external force on them. As far as electrons are concerned, you probably have to take into account the shape of this place where it's touching the molecule, because that probably determines the conductivity. But even in that case, you don't have to deal with the huge numbers of gold atoms that are behind those, in the solid. So look for cases like that. Now I think that's all I have to say. I think I've got some more stuff. Well, I have to actually say, I forgot I had that there. And I have some more stuff that has to do with putting in some Coulomb fields, but I think we don't have time for that. I can leave it on the things we make available if you want. Questions, comment? Oh, good. Yes?
You talk about small molecules, big molecules, and crystal. And how do you do with intermediate size molecule fixed on a crystal? And when it's fixed on the crystal?
I think that one of the greatest things that our community can provide to experimentalists is what is the structure, which is really hard to get experimentally, right? So then I don't know the answer, is number one. And number two is, you could ask, is it fitting on the crystal like, a little like that strained pyramid of atoms that I showed? Meaning that do the atoms in the molecule have to stretch or compress to fit right on top of some molecules in the substrate?
Yes, well, the example I have in mind, for instance, have two anchoring groups which have additional constraints rather than to the molecular arm.
Uh-huh.
So it's stretched to fit on the substrate.
So the part of the molecule is much easier to stretch and move the atoms around than the substrate. So it tries to fit. So you can kind of see that without doing any calculations, right? And then you could, I didn't want to, excuse me, I didn't mean to make that sound simple. It's just that then you could choose that as one of your possible structures, and then really minimize everything else that would be, I guess there's nothing else to do but forces, which would, because you've already made it, you've already stretched it to the proper, or compressed it to fit the substrate. So I guess that would be the equivalent of a solid under pressure, where the internal degrees of freedom will change, but you control it by the external pressure. Sorry, I probably don't have anything good to say. Any other questions? Okay, well, how about you go first?
Oh yeah, now need there be any extra word on, say the gold chain and you break them? So that, I mean, say that was done with DFT, is there anything that needs to be careful of when you're breaking bonds? Or?
Oh, to be careful? Is that what
yeah, to be careful of. I mean, say, you know, using special functionals to cater for breaking.
Oh.
Or because of the large density changes.
I think you're right in the sense that we know that breaking bonds is just exactly the point where we can get in trouble. Mm-hmm. And it's for two reasons. One is it's just a case where the sort of the normal DFT tends to break down because you really have a big difference between a bond and no bond. But also you get crossing of states at just that point. It's when the bond becomes the same energy as a broken bond when you're taking it apart. And when you have states crossing, that's just the place where the density functional is worst. It's worse. Because it was made with one determinant, assuming one kind of system to get a density, and just where you have two degenerate states is where there's severe problems with the density functional. Yeah, breaking bonds is one of the particular problems. Let's see, there was one here first, and then.
I was just thinking, this problem, how far would you have to go into that chain of gold atoms before the effect of the tip stopped being sort of very relevant? If it's, say, 3 atoms long, the same tip is going to be very important. But if it's 1,000 atoms long, then in the middle of it won't care.
So this was a theory simulation that didn't have many atoms, but in fact the experimental case was longer, and I think from all the cases I know, the effect of the outside will really decays quite quickly into something like a gold chain. There'll be special cases where it doesn't decay so quickly.
Right. I was actually not talking about a particular problem, but you know, stress is usually defined as a local force that can be determined by a surface entropy. So when you define it in your Imperial stresses, the definition is that there's a volume.
Yes.
Discrete sum in this case, but still over the entire system. So I was wondering how, if you have any comments on that, rationalizing those two viewpoints, because in the continuum theory, it's definitely a surface.
Okay. I can make a comment that really gets down to this trickiest thing about getting to stress on the atomic level also, because the Schrödinger equation is continuous at an atomic level, so there's great similarities to the Schrödinger equation as a continuous function.
We don't have a Schrödinger equation for nuclei though, in stresses.
Okay, but when you said continuum, you meant continuum mechanics.
Yeah.
Okay, so that is a second derivative continuum equation. Okay, and I think the whole point is that the divergence of a stress tensor is a force. vector, and a vector. And so what you literally find is that this is the definition of the stress in one sense. I guess it's the fundamental definition of a stress, in fact. So you can't determine it except by forces that are acting. And so in particular, you can add any curl to this for the stress, and it has no physical significance. So this would say in a big system, the stress would be constant on the inside and only not constant at the surface. And like for example, if you have a surface that goes from inside to outside, and this is 0, vacuum, solid, then the only place where there's a divergence, is right at the surface. So I think it just absolutely is consistent, and there's just two ways of looking at it. And then I want to emphasize for this class was that for us doing electronic structure calculation, looking at it here is way easier than looking at it there. Somebody over here. Yes?
So just a quick one. Did you say you got a good reference for TDFT and static state calculations for everything?
For this problem?
I think when you were talking about time-dependent density functional theory, you said there was a review paper you got a reference for.
Oh, I said I just wasn't getting to the end of these. So anyway, at the end of the other set of view graphs, I have a set of references for the time-dependent DFT.
Okay.
Yeah. Yes?
When you were talking about the Kalman final theory of forces, and you said it's very easy in plane waves, and it becomes progressively more complicated if you want to deal with basic sets that move on the atomic size. Obviously that adds to later and then we use the same bit of machinery for the stresses later on.
Yes.
Presumably that implies that stresses in a localized basis set are much more difficult, but is it the same order of magnitude more difficult, or does it become completely, how relatively more complicated is it?
There's a sense in which they're easier.
Okay.
But this is where I don't have some experience, so maybe I shouldn't be too glib. But one of the things I thought about saying was that plane waves are easy for forces because they're not attached to atoms. They're actually Poulet forces for plane waves for stress. And that's because plane waves are attached to volume. You stretch the volume and you change the wave vector. So in that sense, plane waves pick up some extra terms in stress that actually cause problems. If you have a finite number of plane waves and you change the volume, then it's not a complete set. And you have an error due to that cutoff. It's just a fact. And so some people have worked on ways to reduce that error. So plane waves are great for forces, and then they actually literally have a problem for stress. And for the localized basis, I guess this depends very much on the problem. But if you, sorry, a second. So the question is, do your localized functions expand or not when you pull it apart? And I think you have several choices. Yes?
You said about TDFT that the successful implementations so far have basically been adiabatic.
Absolutely.
How is that really time dependent? Because isn't that really just moving from steady state to steady state? So can't you lose the model?
I mean, you're right, it's not time dependent at this deep level. So the exchange correlation function is just not time dependent. But the charge density is time dependent. So let's be sure what that means. So, I want to be really sure. So a density, that's a function of time. Really is this explicit time dependence. And And if we talk about anything else, like the exchange correlation functional, in principle, it's a function of the time difference. Because it can't depend on time, per se, but it can depend upon the difference between two times. Right? So we've divided it up and probably used the words in a confusing way, I think. Probably everybody does. But here would be like you take a molecule and you really give it, impose some time dependence on it. And that's what the calculation for carbon-60 was. And we just said time zero, we do something, and then we see what happens later. But if we really put in the true internal workings of the exchange correlation, it must be a function of time difference. So if we assume this is just a constant, then it's still a function of the density at that time. So it's the same functional form, but the density inside it has changed. See, is that okay?
What I was wondering is, when we're talking about those excited states or ionized states, and how you calculate those energies correctly, and you said TDFT could do it. But if TDFT is just in an adiabatic approximation, then would that be any better than if you could know the density exactly, the excited density exactly, and calculate energy DFT? So the difference between those two states?
It might be the same. It's just that what I was referring to, and what I think people would refer to in working in this field, would be: did you need to know all the excited states of the electrons that would give you much, much more than the density? Or did you only have to know the density that results from all those excited states? So you might be able to formulate it in the words you said perfectly well. Anything else?
If there are no more questions, then we should thank you.
Okay, thank you for it's really nice to be with you.